So today, I'd like to start out by making a introduction and very important shout out to my favorite and probably the coolest molecule out there, good old-fashioned H2O, or water. But why is water so cool? Because it's amphoteric. But what does amphoteric even mean? This means that water can act as either an acid or a base, depending on the solution it's mixed into. An example of water as an acid would be adding it to ammonia, which is basic, to get hydroxide and ammonium. So this H2O acts as an acid because it gives a proton over to ammonia to create the ammonium. In terms of acting as a base, if you add water to hydrochloric acid, you get hydronium and chloride. So this H2O acts as a base because it accepts a hydrogen from hydrochloric acid to become hydronium. And that's just facts. While there isn't one specific definition of acids and bases, the Bronsted-Lowry definition is the one that is most commonly used. This defines acids as proton donors and bases as proton acceptors. So a good way that I like to remember this is I just imagine a little acid dude here handing a proton over to his basic friend. And now onto the conjugates. So if you were to mix an acid, a weak acid, with a weak base, you would end up getting a conjugate base from the acid and a conjugate acid from the base. An example of this would be if we were to take a weak acetic acid and add to that water that's acting as a base to get acetate and hydronium. So in this case, this hydrogen here is given to the water to make hydronium. This is an example of conjugate pairs. And that's just more facts. Acids and bases are really easy when it comes down to the basics. It's all about that hydrogen. It's definitely one strong little molecule. You go, Glen Coco. pH is also very important to consider when working with your acids and your bases. And here pH represents the power of hydrogen. Like I said, hydrogen is a very powerful little molecule. pH can also assist us in determining the strength of each of our solutions that we're working with. So if you were to take a look at a pH scale, we have from 0 to 14, and anything under 7 is considered acidic, and anything above is considered basic, while neutral is over here nestled in the middle, just like our little water molecule. And bam, that's just more facts for you. Now, if you were to take a strong acid with a strong base, you're always going to get water and a salt. But wait, salt? Yep, so if you take a hydrochloric acid and mix it with a sodium hydroxide, you end up with a sodium chloride and water. And yep, sodium chloride, that is good old-fashioned table salt. And that's just even more facts. Now, lastly, I want to talk about Kw. Kw is very important when attempting to calculate pH, and it can also help determine types of buffers and titrations. So here, this is the constant for water when it's at equilibrium. And Kw can either be equal to the Ka, or the acid constant, or Kb, or the base constant of dissociation, or Kw can be equal to the concentration of an acid multiplied by the concentration of a base. And that's in facts.